Alright, we're looking at this problem. It wants us to know what is the major product obtained when 2-nitrothreophene reacts with bromine. Alright, now, had this just been the threophene, the answer is with the bromine is just, it's going to definitely go in that 2 position because that's the most active location on our 5-membered rings. And we wouldn't necessarily need a Lewis acid on this electrophilic aromatic substitution because that sulfur has made that ring so much more active. All right. Now, the trick happens on this, and the tricky part happens because we have added, actually, a deactivator already in one of the 2 positions. Now, had it been an activator, or anything that's relatively active on a standard benzene, the definite product we would have got was over here. But in this case, we get a small problem that pops up. So I'm going to have the nitro over here, but I'm going to expand it and do what it looks like. So that's kind of negative and that's positive. And this is still going to be a double bond, but I'm going to show our bromine attaching with the hydrogen still there. So our reactive intermediate, which makes that a positive. And then we'll show how that can move over and help stabilize this. So one of our resonance contributors. That's where that positive would move when it swaps. But now we have a problem where that is adjacent to that positively charged nitrogen. And that is a very unstable species. Now, that doesn't mean it doesn't happen. It just means there might be a better location. Now, technically, we do have one other resonance contributor here, and I am going to go ahead and bother to draw it. So we do have 3 relatively stable resonance contributors for the reaction when we put the bromine in this location. That would still be a double. This is actually going to be a double. Putting the positive on the sulfur. So we do have 3 resonance contributors, but one of them is very unstable. So because of that, we do need to, we are going to check the other 2 locations and see if one of them is better. All right, so, and we do need to check them both. We can't just find one that we like. We need to do both possibilities. So I'm going to show our first one. And I'll put the H and the Br here, which would cause that location to get our cation. And then our only resonance contributor is those lone electrons dropping down in. So this location only gives us 2 resonance contributors that are stable, but both of them are perfectly stable. We don't have an excessively unstable location where the positives and negatives are on top of each other. But if our other location gives us more resonance contributors, that's actually going to be the one we go with. So there. Oh. And the NO2. And the first resonance contributor we get is going to expand this just like normal. That would still be there, the still lone pair. We'll have our H and our Br in that 3 position, which causes this to be a positive. And we have the 2 positives right next to each other, so this is unstable. Now we can stabilize it a little. By putting that double bond here and the positive on the sulfur. But because of that unstable and because of this unstable, we actually know that that's the one that's going to lead us to our favorite product. So our product we're going to expect from this reaction with a nitro there, nitro, is nitro here, bromine actually there. That would be our major product because it is what we get from the most stable resonance contributor or complex.